topic for this video is acids and bases. So a few different scientists came up with some different definitions for what an acid is and what a base is. So we're going to learn a couple of them. The Arrhenius definition, which was developed by a scientist named Arrhenius, said that the acid was a source of hydrogen ions. For example, hydrochloric acid has a hydrogen that it could give away. He said that a base was a source of hydroxide ions. For example, sodium hydroxide has hydroxide it could give away. Bronsted-Lowry had a different definition. They said that the acid was the proton donor, so that's not very different because a proton is an H+ ion. But the base is a little bit different. They said that the base was a proton acceptor. Okay, so this is how that would work. If you mix hydrochloric acid and water, so the hydrochloric acid has a hydrogen here and a chlorine here, and it could donate a hydrogen to the water. Then over on the right, it becomes H3O+, so it has an extra hydrogen, and chlorine minus, so it lost the hydrogen. So in this case, the hydrochloric acid is the acid because it's donating. And I know water is neutral, but sometimes water can act as an acid or a base depending on what it's combined with. In this case, it's a proton acceptor, so according to Bronsted and Lowry, this is a base. Let's look at another example, again with water. This time we have ammonia. Okay, so in this case, water is going to give a hydrogen to ammonia, so it can become the ammonium ion. So because ammonia is accepting it, that's a base, and water is donating it, that's an acid. So water can act as an acid sometimes and a base other times, and other times it's just neutral. So that's called being amphoteric, which means it can act as either an acid or a base. So water is our main example of something that's amphoteric, but there could be others. So we're going to do some sample problems, and we're going to identify the acid and the base according to the Bronsted-Lowry definition of donating and accepting. And then we're going to identify the conjugate acid and conjugate base, and I'll show you what that is as we go through the examples. So if we look at this problem from left to right, we look at HCO3, and if we look on the other side, it has become H2CO3. That means it's accepted a hydrogen. If you look at the H2PO4 on the right, it has become HPO4, which means it's lost a hydrogen or donated it. So we can see that a hydrogen has gone from the H2PO4 to the HCO3. So because of that, the H2PO4 is the donor, which in the Bronsted-Lowry definition is an acid, and the HCO3 is accepting, so that makes it a base. On the other side, if you think about going in reverse, okay, the H2CO3 would be giving back that hydrogen, so that makes it the conjugate acid, and HPO4 is accepting, so that makes it the conjugate base. So the acid and base are always going to go on the left side of the equation, and the conjugate acid and conjugate base will go on the right. Okay, so let's look at this. We have HCN, and it's going to give an H to the PO4, and you can tell by looking at the right side that it has become HPO4 and just CN. So that means that HCN is giving, so that's the acid, and PO4 is receiving, so that's the base. On the other side, it's reversed. The HPO4 is giving to the CN, so that means HPO4 is giving, so it's the conjugate acid, and CN is receiving, so it's the conjugate base. So we have something called a conjugate base pair. So if we look at HCN, and then it says /CN minus, and then we have PO4, and it goes with HPO4. These are called conjugate acid-base pairs, because on one side of the equation they're the acid, and the other side they're the base. So if we look at the next one, HNO2 becomes NO2, so it's losing, so it's an acid, and OH becomes H2O, so it's receiving, so it's the base. So that means that on the other side, you can kind of start to see a pattern. Whatever was the acid on one side becomes the base on the other, so it's a conjugate base is NO2, and OH was the base on one side, so it becomes the acid on the other, so H2O becomes the conjugate acid. So that means one conjugate acid base pair is HNO2 with NO2, and another one is OH with H2O. If we look at the next one, HSO3 becomes H2SO3, so it's accepting. So it's going to become the base, and CH3NH4 plus just becomes NH3. So it's going to donate, it's the acid. On the other side, it's reversed. So because the CH3NH4 was the acid, now CH3NH3 is the conjugate base, and HSO3 is the base, so now H2SO3 is the conjugate acid. So we have HSO3 and H2SO3 going together, and CH3NH4 plus and CH3NH3 going together as the conjugate acid-base pairs. Okay, so there's something in acid and base chemistry called a buffer, and this is a conjugate acid-base pair made from a weak acid or a weak base. And you can see in the picture kind of what it's doing. It kind of bonds to if you have a strong acid or base. It keeps the pH of a solution constant even when you add small amounts of acid or base to the solution. For example, ammonia and ammonium chloride are a buffer together. Acetic acid and sodium acetate are also a buffer that can be used. Alright, so we're going to practice identifying the formula of the conjugate acid, and you'll notice a definite pattern here. So the conjugate acid is going to have accepted a hydrogen, so it's going to have one extra hydrogen, and a hydrogen is a +1, so it's also going to alter the charge. So HCO3 is a -1. So first of all, we add an H, so it becomes H2, and when we add an H, we add 1 to the charge, which brings us to neutral. CO3 is a -2, so we're going to add an H, and that becomes HCO3, and we're going to add 1 to the charge, so instead of a -2, it's just going to be a -1. H2O is going to become H3O. The charge was neutral, so now it's going to be a +1. NH3 is going to become NH4. The charge was neutral, so it's going to be a +1. H2PO4 is going to become H3PO4, and that charge is -1, so now it's neutral. And SO3 is a -2. It's going to become HSO3, and we're going to add 1 to that charge, so it's a -1. So now if we look at doing the opposite, identifying the formula of the conjugate base. Okay, now we're going to take one H away, and we're also going to subtract 1 from the charge. So HCl, we're going to take that H away, and so it just becomes Cl, and it was neutral, so we're going to subtract 1, and we get Cl-. H2SO4 is going to subtract an H, so we have HSO4, and it was neutral, and we subtract 1, so it's a -1. HSO4, we can take another H away from that, and we get SO4, and it was a -1, so now it's a -2. HPO4, 2-, we can take off that H, so we get PO4, and subtract 1 from the charge, and we get -3. NH4 plus, we take an H away, and we get NH3, and take 1 away on the charge as well, and we get neutral. And H2O, we're going to not write it HO, but write it as hydroxide, which is OH, and it was neutral, and we subtract 1, so it becomes a -1 charge. Let's go through some of the basic properties of acids and bases. First of all, the pH range we talked about is 0 to 7 on acids. On bases, it's 7 to 14. The concentration of H and OH comparatively, on acids you're going to have more hydrogen. On bases you're going to have more hydroxide. The color of the litmus paper is going to be red on an acid and blue on a base. So this is an indicator. On phenolphthalein, which is another indicator, it's going to be colorless on an acid and pink on a base. Some other things, acids corrode metals, which means they're able to react with them. And bases tend to feel slippery. Acids taste sour, like if you think of citric acid, like limes, lemons, oranges. And bases tend to taste very bitter. Think